Oh yeah, that's a good point. Yeah. Okay, sure. Hi all. My name is Glenn Hibbard. I'm a professor in the Department of Materials Science and Engineering, and I'm going to talk a little bit about some of the research that we do in my research group today. And it's going to kind of go through some stuff that have done in the past, some things that we're doing now, and some things for where we're going in the future. So let's say with respect to past things, we've been really interested in the question of how do you design optimal material structures. So for example, one of the things that needs to be created are lightweight structures that can resist large loads but are very efficient. So this could be for applications like in the aerospace sector. So one of the questions we looked at in my research group was, how do we build the lightest, strongest material that we can possibly imagine? That means kind of looking at the question from two perspectives. One side is we need to be able to make something strong. And so making something strong means we have to be able to control the relative motion of atoms with respect to each other. Because it's the motion of atoms as they start slipping past each other. It's when materials go to fail. So we have to be able to control that aspect. And the other side of it is, if we want something to be lightweight, then we need to be able to incorporate open space into the geometry. So we want to make something that's going to be a hybrid of, let's say, a strong metal and open space. And that's what a couple of these examples are. So this was an early example of something that we worked on. This is a type of foam. It was a polymer foam, and then we put a metal coating on it, and then we electrodeposited a very high strength nanostructured layer on top of it. So this becomes a very rigid structure that has a good degree of efficiency. We can do a couple of steps better though, but instead of having a disordered structure like this, we can make something that has a regular geometry, like this guy, has a little truss structure. And new manufacturing techniques over the last, let's say, decade and a half have allowed us to, with 3D printing, additive manufacturing, that kind of stuff, we can build templates, and then upon those templates we can electrodeposit, for example, really high strength metals. And so that lets us build structures like this, and we have a very large degree of control over the shapes that we're building. And so as soon as we have that large control over the shapes, that poses a really interesting question for us, because then we got to be able to decide what's the best shape of material to produce. And so that starts to get us into the question of optimization. So optimization would mean, for a given application, what is the best possible way that we could arrange all of the material inside of something to meet, let's say, the particular design objective. However, that's not necessarily all we want to do. Maybe instead of just making something that's going to have a high strength to weight ratio, maybe we want to make something that's going to have a high degree of environmental sustainability. One place in existing structures there are sandwich panels that are used all throughout industries. This is a little example of a sandwich panel, one that we've made that would be sort of like a sustainable alternative. So in typical sandwich panels, you have several materials together, and problem with that is that once let's say this panel has gone past its lifetime, let's say we've used it for whatever application we needed, we don't really have any way of separating those materials apart and then recycling them. So it ends up becoming sort of a dead-end material. It's really only good for the landfill afterwards. And what we wanted to do was to try to tackle that problem and make something that would be sustainable. And so that's what these little pieces are. This is a process that we've developed in the group to take molten polymer, have it between metal plates, squish it together, and then stretch it out. And by controlling the boundary conditions around that kind of where this stretch happens, we can get the structure to form some of these interesting shapes. So here we have like a range of hexagonal and square and triangle kinds of geometries inside. We've got quite a bit of flexibility and freedom in choosing that, and that gives us a very rich design space from which we can try to optimize something. So that's one of the things that we're working on now. I guess kind of in stepping forward into some of the things where we're going and stuff that we're interested in, it's taking that kind of question and then generalizing it and abstracting it one layer more. And so looking at the nature of information and materials itself, and how does material information sort of go to constrain and define and limit what we can do and how we can try to build optimal structures. That's sort of in a nutshell some of the things we're interested in. You can explore through the webpage here, and you can find some of the other projects that we're working on, and there'll be other little videos that will tell some of that story.